to go. Count out or circle your main chain, I think, is the most important thing. We got 1, 2, 3, 4, 5, 6, 7. So we're hept. Our carbon functional group, or our alkyl functional group, is all sp3 hybridization, so we can say an. We have a ketone, so it becomes heptanone. The issue there is we need to specify where the ketone shows up. We put it at the shortest chain number, so we've got 1, 2, 3 heptanone. The other option is to drop the 3 into the backbone of the name. Okay, you don't need to do that. 3-heptanone works perfectly all right. For the next one down, same idea. You want to circle the longest carbon chain, but our caveat in this case is that you have to circle the largest carbon chain that contains the highest priority functional group, which means we're circling here. And we have, what is that, 1, 2, 3, 4, 6 carbons. So hexane, because it's all sp3 hybridized for our carbon chain, it's an aldehyde, so we call it an al. And at the 1, 2, 3 position, we have a propyl group. Why do we not specify the 1 for the aldehyde? It's implied. Okay? Aldehydes, by definition, will be at the end of a chain. You don't need to specify the 1 for the location of the aldehyde.
3 or 2?
You're right, 2. I wrote 3 because it was propyl. It's 2 propyl hexanyl. All right, 1, 2. The next one down, we've got 1, 2, 3, 4, 5, 6. We've got another hex. Notice any patterns? Apparently I can't count higher than 6. Primarily sp3 through, so we've got our an adjustment. The higher priority functional group is the aldehyde. Okay, so we end with the al ending for our aldehyde. We now also need to specify the location for the ketone. Okay, because the ketone is not our primary functional group, we include it in the front as an oxo, and is located at 1, 2, 3, 4 oxo hexanal. Again, you don't need to specify the 1 for the aldehyde. For our last one, which is a bit of a beast. 1, 2, 3, 4, 5, 6, 7. Apparently I can count high up to 7. So we've got the hept, but is it all sp3 carbons through there? No, we have that alkene, so we'll end up changing it to an ene ending. We would need to specify where in our structure the alkene showed up. Okay? So that means evaluating its priority as far as the numerical system. So I'll skip that for the moment and jump to the other primary functional group on there, which is our aldehyde. So we'd have the al. And then we also have the alcohol. The aldehyde takes priority over the alcohol. So the alcohol comes in as a hydroxy, which I'm going to run out of space for. Hydroxy. And we have a methyl. And now we've got this numbering system. Our numbering system is always going to start closest to the highest priority functional group. The highest priority functional group in this case is the aldehyde. So that's our 1, 2, 3, 4, 5, 6. We could, again, drop the 1 in there for the aldehyde. Again, not necessary. You can run that all together. The alkene showed up at carbon number 6. The hydroxy and the methyl both showed up at carbon number 4. So what we would end up with is 4 hydroxy, 4 methyl, hept 6-ene al. Okay? The order on that, hydroxy needs to come before the methyl because alphabetical order in that respect. Does that answer the questions? I believe that was Will and Ryan that asked for those two. You guys okay with that? officially, between a number, you have to include a dash, and then you can do your letters. If you have another number show up, you need another dash. Okay. If we have multiple numbers, you need a comma between the numbers. So it's a bit hard to show it on this because I stacked it, but you'd have 4-hydroxy-4-methyl hept 6-ene al. Okay? Kind of, sort of? Okay. Remember, you should be continuing to work on your nomenclature. I will try to remember to bring it in every so often. In theory, every lecture, that's probably not going to happen. We'll probably get it once a week at best. Okay. There was a request from Jimmy for looking at kinetic versus thermodynamic again. Okay. Absolutely fair game. It's a hard concept to deal with. I will try and record a mini lecture on that, and I'll look at the 3 cases of kinetic versus thermodynamic that we've seen so far. Our conjugate addition with our alkenes, okay, with HBr. I'll go through that example. I'll go through the Diels-Alder example, and I'll drop in the enolate formations, which we just saw recently. Okay? And by the end of chapter 17, we're going to have a 4th. Okay? They're all ultimately looking at the same idea. You just have to be careful at what stage you're trying to get to. So I'll try and put it all as one big thing so you can see the parallels, hopefully, through that. We talked about this one already, our active chemistry on a carbonyl. We've got the lone pairs on the oxygen giving us a nucleophilic characteristic. Because that carbon is attached to an electronegative oxygen, we have an electrophile in that carbon. Hidden chemistry, we have the alpha position. That hydrogen is also partially acidic, and actually quite acidic, which is due to resonance. There's a resonance stabilization of that structure. Okay? Once we remove that acid, then what does that carbon become? Yes, it becomes basic. True, fair enough, good call. And, more importantly, nucleophilic. Okay. Which, for our top nucleophile, it could also be a base. Within that discussion, you'll notice that we didn't really talk about the pi bond. Okay. The pi bond, potentially, arguably, is the most reactive nucleophile in this case. It's so polarized that we end up almost ignoring the pi bond and looking at the lone pairs on the oxygen acting as our nucleophile. Okay. So it's a primary characteristic of our carbonyl chemistry and ultimately our polar pi bonds. Okay. So any case where we have a polar pi bond, we end up seeing this same kind of similar chemistry. So for instance, if we switch this functional group up to instead this guy, what functional group do we have? It's not an alkyne because it's got the nitrogen in that. So it's a nitrile. You might also see it referred to as a cyano. Okay. We have the same chemistry in the nitrile as we do in the carbonyl. We have that polar pi bond because that nitrogen is more electronegative than the carbon, which means our carbon becomes electrophilic. Our nitrogen becomes nucleophilic/basic. Our hydrogen at that alpha position becomes acidic, which could then potentially lead to us having an active nucleophile. Okay. So it's looking at the commonality between the functional groups, not their differences. Is it a polar pi bond? Yes, all of this chemistry falls out of it. Okay. What chemistry do we get for this functional group? Anybody know what the imine looks like?
Two hydrogens.
There's an imine. What do we see within the imine functional group? A polar pi bond, guess how it reacts? Same way as our carbonyls. Right? So anytime you see these functionalities, that's what you should be looking for. Not carbonyls react this way, and now that's the only thing I know how to react. Okay? An imine is, for all intents and purposes, a carbonyl. Okay? So its chemistry is very, very similar to the carbonyl. There are some changes which we will address when we get to them. For the most part, they are the same functionality. So when we're looking at chapter 17, what we're going to evaluate is the reactivity of our carbonyl, whoops, there it goes, as an electrophile. That's the primary source of chemistry in both 17 and 18. Okay? In 17, what we're doing is reacting strong nucleophiles with our electrophile. They're so strong that it centers at that carbon. In chapter 18, we now move to weaker nucleophiles. Okay, those weaker nucleophiles, because they are weaker, now react slightly differently, and we have to take that into consideration when we look at these functional groups. Okay? So, within chapter 17, we've got our hydrides. We have the Grignard reaction. I don't think I'm going to talk too much on the acetylide. We have the Wittig, and we have the Gilman reagent. You'll notice that what all of those have in common is that you are putting a negative charge on an element that cannot hold a negative charge. Okay? Because hydrogen and carbon are both very low electronegativity, meaning they don't want to hold on to those electrons, and they're also very small. So nothing about those atoms can stabilize the negative charge very well, which makes them incredibly reactive. Okay? Our general mechanism, when we're dealing with our polar pi bond, we've got our nucleophile, and under this condition, what chapter do you think we'd be looking at? Chapter 17 or chapter 18? 17, because it's a strong nucleophile, because we see that negative charge. We'll run into issues with what strength means when we move into 18, but this at least gets us a first pass. When we look at our carbonyl, we can look at the resonance structure to help us identify that positive and negative sites of reactivity. Our nucleophile will go the most positive atom. You'll almost always see the mechanism with the carbonyl. You'll see this version of the mechanism. Very rarely will you ever draw out the resonance structure and then see someone draw the nucleophile attacking the carbonyl or the carbocation. Why? Why is that never shown? It's not a substitution. The end result is exactly the same. There is no difference in the end result. Why do we not show the purple method? Why is it only the red method? It's kind of along those lines. Which resonance structure is the better structure to show? The top one, because there's no charge. Drawing the resonance structure helps you identify the chemistry. In a case, particularly like our online homework, they don't care that you can identify the chemistry, they care that you're showing the electrons connecting the proper way. Okay? And they're only going to fit you within certain boxes, which means you need to minimize your drawing as much as possible. Okay. Once our nucleophile is attacked, we generate a negatively charged oxygen. Okay, and we might say, well, negatively charged oxygens are a bad thing to have, and you would be correct. But what is our nucleophile, particularly in the context of chapter 17? A negatively charged hydrogen or a negatively charged carbon? Where would we rather have the negative charge? On the oxygen. That's why our reaction can drive forwards. Okay? We are stabilizing the reactivity of that nucleophile. At this point, our reaction stalls. There's nothing that we can really do to stabilize that negative oxygen until we follow it up with a workup step with H+. Depending on the reactivity of our nucleophile, we may or may not specify this as an extra step with H+. In the case of chapter 17, you almost always see H plus added as a second step. And that is because the reactivity of both the hydride and the carbide nucleophiles is so high that we need to add it as a second step to very clearly show they're in separate systems. But if, for instance, we shift to a weak nucleophile, now we don't necessarily really care what's going on with the acid, okay? Where it's coming from or where it's going. So if we run under a weak nucleophile system, something has to come through to activate the carbonyl so that it can react. That's why we add the acid. The acid reacts with the oxygen of our carbonyl first. That really polarizes the pi bond so that we can get that carbocation. Now the weak nucleophile can come in and react with it to generate an intermediate. Remember, since it's weak, we probably also have a hydrogen still floating around, okay, attached to the nucleophile. That gets removed by anything remotely basic. Which is why when you see me draw the mechanism, you'll notice I don't show the thing that is removing it. Okay? Up to you. If you want to follow me, great, it works. Okay? If you don't want to follow me, that's fine. Just be aware that if you write this on an exam, you will get marked wrong. Why? Hydroxide is a strong base, and you started the whole process off by saying we were in an acidic environment. Okay? So we have to be careful with the formation or introducing species that are reactive with any of our intermediates. If we run under acidic conditions, we better make sure that all the way through our mechanism, we maintain that acidic condition. We can't throw in the opposite. If we run under basic conditions, we better make sure that we maintain through the whole mechanism basic conditions. Okay? The one exception on that maintenance is in your very last step, you can do pretty much whatever you want as long as you don't add a strong opposite of whatever you are working with. Okay? Kind of makes sense?
So what would be the best way to show that?
The best way to show that bottom reaction is exactly like that. The electrons between the hydrogen and the nucleophile go to the nucleophile. I should have drawn that product a little bit better. You'd see the lone pair on the nucleophile, and you'd see an H plus out here. Typically, just as was drawn here, we don't see the H plus. Why did I not draw the H plus? It has no carbons attached to it. I don't care. It's not organic. Okay? So we end up dropping off those reagents or intermediates that aren't organic. Okay? The only time you need to include them is when the question specifically asks for it. That would be in your workup. So that last step there is likely coming from the workup of the reaction. And during that workup, you would need to neutralize whatever was in there. You'd neutralize the H plus with a weak base. Boom. You've now fixed your protonation issue. Okay? I will try my best to identify in every reaction we do when the workup happens within the mechanism. I can't guarantee that I'll remember, but I will try my best. Okay? We've got a nice little spider diagram here. This has everything from chapter 17, all on one big hairy slide. And it includes the acetylides, which aren't in chapter 17, technically. But these are all the reactions that come out of chapter 17. You'll notice in that top half, what happens? We add a nucleophile and it reacts at the carbonyl carbon. Nucleophilic carbon attached to the carbonyl carbon. Nucleophilic hydride attached to the hydride, or to our carbon that was then implied. Son of a. Okay? Hydrogens typically get implied. Watch out for those. Where did the hydrogen come from to protonate the alcohol? Or protonate your negatively charged oxygen? It came from our solvent, which was an alcohol. Okay. When we moved to lithium aluminum hydride, our hydride attacked the carbonyl carbon. Where did that red hydrogen come from? Acid, which happened to be in the second step. You'll notice, borohydride, there's one step. Lithium aluminum hydride, there's 2 steps. Those of you in lab, why? What is different about borohydride from aluminum hydride? The reactivity of your borohydride and your aluminum hydride. Borohydride is much less, sorry, I gave it away, much less reactive, and the aluminum hydride is much more reactive. The aluminum hydride is so much more reactive, we can only add that acidic hydrogen in a second step. Grignard reagent. We end up adding an R group as a negative charge. You'll notice you don't see the formal negative there. It's hidden, but it's there. We'll talk about it. You'll also see, whoops, please connect. So our R group again attacked the carbonyl, and our hydrogen came in the second step. Why did it have to come in the second step? The reactive carbon nucleophile. If it came in the initial step, that nucleophile would act as a base instead, okay, and deprotonate as opposed to acting as a nucleophile. Next big one, very similar chemistry. You're looking at your organolithium reagents. I broke that down in individual steps so you could see how to make them for that one. We also have the Wittig reagent, which, in all honesty, I'll be perfectly frank on this, instead of Mike. Okay, thank you, Matt. The Wittig reagent, I do not know anything, or did not learn anything about this reaction where it actually stuck in my head until 2 years ago. And I've been doing chemistry for 15 years. Okay? So, some reagents you just don't remember. I now remember the Wittig reagent because I've had to talk about it too much. Okay? So you may forget these, realize you're tested on all of them. Okay? So you got to keep working through them. Interesting thing on the Wittig, what happened? What functional group do we end with? Carbonyl on the Wittig? Oh, we had an alkene, not a carbonyl, not an alcohol. The Wittig reagent is so reactive that what did we do entirely to that oxygen? Kicked it to the curb and got rid of it entirely. Neat little reaction. The last part of chapter 17 modifies the functional group. Instead of looking at just a standard carbonyl, we change it to what is known as an alpha-beta unsaturated carbonyl. Where's the alpha position? It is 1 carbon away from our carbonyl. There's an alpha position. There's an alpha position. Where would the beta position be? The very next carbon, which I only drew in one case. So that is now the alpha-beta position. And it says unsaturated. What does unsaturated mean? You remove the hydrogens, which means you necessarily have a double bond. So an alpha-beta unsaturated carbonyl means you have a double bond conjugated to a carbonyl. Okay? Why does that change things? Well, that's actually a good question. How many of you drew one resonance structure? Okay. For those of you that drew one resonance structure, is the red carbon a positive charge? Did anybody draw the resonance structure where the red carbon was a positive charge? Did you draw another resonance structure? Holy crap. Damn. Well, that takes all the fun out of that. Good job. If we look at our resonance structures, we do have the option to pull the negative charge in that pi bond out onto that oxygen. We have a negative oxygen and our carbon becomes formally positive. We also have the additional resonance structure of bringing the pi bond from our carbon out, and we would end up with this structure with the positive charge on the blue carbon. Why does that become important? Our starting material now has 2 sites of electrophilic character. It's good enough. Okay. Which means, where does our nucleophile attack? Well, that discussion comes down to what is your nucleophile. If you have a strongest nucleophile, that's your hydrides and your carbon negatives, Grignards and Wittig reagents, it attacks the carbonyl carbon. If you have a quote-unquote strong nucleophile, meaning it's not as strong as our strongest, it attacks the beta position of our alkene structure. That line seems very arbitrary on where you classify. Unfortunately, it's something that comes straight out of the lab. We went into the lab, we tested a nucleophile, it did the carbonyl, so we called that one a carbonyl one. Okay, but as we start to weaken the strength of the nucleophile, eventually it switches to the other side. Okay? It's not a super clean, hard, fast black line that you can say, this is really easy, this is why it switches. What ends up happening is it starts to progressively get to a point where it reacts at both sites, and then eventually it only reacts with one site. Okay? So be aware of that when we move into that section. What we try to do is give you reagents that force only one chemistry or the other, not both. Why not both? We could say it's confusing enough. What did you say?
It's going to get unpredictable.
It's going to get unpredictable. Our whole point is to be able to predict the products that we get out of a reaction. If it's unpredictable, that's a pretty lousy reaction to do. Okay. Reactivity of carbonyls. Do all polar pi bonds react the same? They may have the same general idea on the mechanism, but what happens to, say, the speed of the reaction if we change the carbonyl? So we got the idea of what happens, but how fast does it happen? Would we predict all of these to react the same, at the same speed? Okay. I'm seeing one person shaking their head no, thank you. Okay. Now the question becomes why? How polar what bond is? Okay, well, the double bond is between an oxygen and a carbon. We look at those first 3 examples, where's the double bond? Between an oxygen and a carbon. So that's fair enough, because we can look at the last ones, carbon and nitrogen. What's our difference there?
A little bit less electronegative.
Nitrogen is less electronegative, which means what happens to the charge on the carbon?
Less positive.
Not as positive, which means we might expect those to react a little bit slower. Okay, but what about the first 3?
There's resonance potential with the 2
We're changing the R group, so we're looking for that difference. What makes those different from each other? We're looking at hydrogen versus an R group being ultimately a carbon. What is the difference between hydrogen and carbon? Electrons. Carbon has more electrons, which means what does that carbon do? It stabilizes the charge, making the aldehyde and the ketone slower to react than that first one, which is formaldehyde. Okay. Do we end up indeed seeing this? Yes. If we go through and react all 3 of these, and this is a bit of an odd table to include in this chapter, but if we go through and react all of them under the same conditions with a weak nucleophile, the oxygen of our water comes in and attacks the carbonyl carbon. And if we go through and look at the rates and the amounts of each of those products at equilibrium, you notice that we end up seeing a very high concentration of product in the case of the formaldehyde and a very low concentration in the case of the ketone. Why? The carbons in the case of the ketone, donate electron density in, making the carbon less reactive to our nucleophile, which then slows that last step. Well, if that oxygen can't come in and attack, can I make any product? Nope. So I would get a very low concentration of product. My rate is also incredibly slow in comparison to everything else. Okay. So when you look at your structures, it's not, oh, I have a carbonyl, let's just do it. Look at how everything else around it can affect the reactivity, because those subtle changes make a big difference in the end result. I added another one on here. What do you think? More or less reactive? Remember we said the nitrogens were likely less reactive than our oxygens, so we started to increase in reactivity from right to left. What do you think happens with this new addition? Why is chlorine electron withdrawing? Okay, but doesn't it have electrons that it could donate via resonance? Technically, those are electron donating. Our halogens end up being in a very weird kind of subcategory. Turns out that under this circumstance, guess what happens? The chlorine primarily acts as an electron withdrawing group. That species becomes incredibly reactive. Much the same way that we saw for this. Whoops. No, don't previous slide me. What are you doing, you stupid thing? Much the same way we saw for this guy, our thionyl chloride. That sulfur was now incredibly reactive because it had 3 electron withdrawing groups. Okay? That helped it act as a wicked good electrophile. If we now swap that in for a carbon, it's now an even better electrophile. Okay? So the context of why we care, this comes down to our nucleophiles. There are certain circumstances where I can have different sources for the same nucleophile. Say like hydride. How many different ways can I get hydride into my reaction? You got sodium hydride, you got lithium aluminum hydride, you have sodium borohydride. There are a bunch of different ways to get it in there. Depending on our starting material, we may choose a very particular hydride source to get the end result that we want. Why do we have to change? Because the reactivity of those functional groups of our electrophile also changes. Okay? Which gets us to our hydride. Incredibly fun slide here, right? We got the Lewis structure for hydride. How stable is that? Don't shout it out all at once. I know I drew it really big. How stable is hydride? Not stable at all. Incredibly tiny, concentrated charge, not electronegative, incredibly unstable. Okay, so I can't just add hydride in. So I'd have to add something with it to stabilize it. So if we had switched this to, say, a different nucleophile, strong nucleophile like hydroxide, how could we temporarily stabilize our hydroxide to make sure we get that chemistry still in our reaction? How do we add hydroxide to a reaction? We threw a metal on the end of it, and we have sodium hydroxide. Sweet. Okay, so let's do that with our hydride. Let's have sodium hydride. Okay. That does temporarily stabilize the hydride. However, that stabilization is incredibly not very good, okay, for lack of a better description. What does that mean? That hydride is now very, very reactive even still, meaning I open up the container of sodium hydride in the atmosphere, particularly around now. What happens? The hydride, now being so reactive, needs to find a positive as quickly as possible. What's the most readily available positive? Water in our atmosphere. Hydrogen from water reacts with the sodium hydride to form hydrogen gas, neutralizes the hydride permanently, and we now don't have a very good reagent. Right? So that becomes tricky when getting it from our reagent bottles into our reactions. We push it further, we get it to the reaction. What's its solubility going to be in any of our organic solvents? Horrible, which means it's going to stay a solid. The only place it can react is on the surface of the solid. Sterically, sodium hydride very counterintuitively becomes massive, which means it cannot act as a good nucleophile. Well, we said we can get hydrogen nucleophiles, so we have to come up with another way to stabilize that negative hydrogen. How can we do that? We need to find some species that is willing to accept some electrons, right, but also be willing to give them back immediately. There are certain elements on our periodic table that work perfectly for this. And those would be in group 13. Okay. You'll notice boron and aluminum, if we pull out their Lewis structures, particularly if we did BH3, have what hybridization? sp2, which means what is left over? An empty p orbital. What can I put in that empty p orbital? I can put electrons from my hydride. That will stabilize the hydride well enough that it is now stable in the atmosphere relatively, that I can get it into my reaction, and it will now act as a nucleophile because this species will dissolve in some of our solvents. Okay? Kind of a neat little ditty we can do with that. So, two big reagents that you need to know. Sodium borohydride and lithium aluminum hydride. Okay. Both of them will do the same chemistry. They put that hydride in, they react to the carbonyl, we get a shift. Okay. Or we don't get a shift, we get our alcohol product. So we've done a reduction reaction by adding hydrogen across the double bond. What are the differences between these two reactions? What do you notice? We got 2 steps. Way to pick the easy one first. Good call. Now it gets harder. Say that again? So the source of hydrogen to protonate our alcohol is slightly different. In one case it's acid, in one case it's water. Yeah, sure, let's count that as a difference. I can work with that. 83 versus 80, come on. That's not that big of a difference. I mean, that is technically a difference, but let's see if we can find something bigger. Okay, we could look at reflux. It's another option. And now you guys you're definitely going off on the path of like looking for way nitpicky details. It's not that nitpicky. How about one of them uses sodium and one of them uses lithium? How about one of those uses boron, one of those uses aluminum? Those kind of differences are going to impact how these react. Okay, the question now becomes is why? Okay, so the H+ issue, our last one is 2 steps. Okay, we end up adding H+ as a secondary step, where in the first one we don't add H+ directly, and we also don't have a second step. What does that suggest about the reactivity of the lithium aluminum hydride? It is very reactive, that if we put it in the presence of an acid, it dumps off the hydride as a base instead of as a nucleophile. What does that say about our sodium borohydride? Not as reactive, which is actually better for us because we can now control its reaction a little bit easier. Okay? More control, less danger, that's in general a good idea. Okay? What's the next difference? Well, sodium versus lithium. What's the difference between sodium and lithium?
Size,
Size. What is that size going to do?
stability,
It's going to have to contribute to stability. Okay? What charge are both the sodium and the lithium?
positive.
Okay, so in the course of this reaction, in most reactions, we would say what happens with our sodium and our lithium? When was the last time you saw me write out sodium ion in any reaction? Okay. Very rarely do we look at it. We almost always just ignore it altogether. We call it a spectator ion. It is actually important to evaluate the difference in reactivity between these. What do we need to have that positive react with? A negative. It's starting reacting with the hydride negative. Okay? So what would it then move to? The oxygen. In the case of our lithium aluminum hydride, we can coordinate our lithium up to that oxygen, or we can coordinate the sodium up to that oxygen. How does that change the reactant? Lithium is smaller, it binds to the oxygen tighter, which means what happens to the electrons?
They're going to shift back towards the proton.
Okay. What happens to the electrons in that carbon-oxygen double bond if the lithium binds tighter to the oxygen? Lithium is now saying, F you, oxygen, I'm taking your electrons. What does the oxygen say? Could say, yeah, right, and it'll fight back a little bit. Or it can take them from the pi bond, which means what happens to the charge on our carbonyl carbon? It becomes more positive. Okay? So just a swap of the counter metal, the metal ion that we never ever draw out in our reactions, by switching to a smaller one, we polarize that pi bond further, which then makes our carbonyl even more reactive. Okay? So just if I, instead of using sodium borohydride, I move to lithium borohydride, guess what happens? Becomes more reactive. Okay? The next one, which is our larger difference, aluminum versus boron. What's our difference there? If aluminum is bigger, what is it doing to the bond distance between our hydride and the aluminum? The distance between the hydride and our aluminum gets very large, whereas in the boron, it's relatively small. What does that mean happens to the reactivity of our hydride? It becomes more reactive, it is less tightly held, it now increases its reactivity. So our lithium aluminum hydride, for multiple reasons, ends up being incredibly more reactive than our sodium borohydride. Kind of makes sense? All of that chemistry centers on the electron configurations, our Lewis structures, for both aluminum and boron. They have that empty p orbital. They can accept the electrons from the hydride temporarily to stabilize it. Okay. Once we then dump it into a solution that has a good electrophile, it can ditch the hydride and it goes back to being happy as just aluminum with 3 hydrogens-ish. Okay. Questions on that?
Like intermediate, where you're having the boron with the lithium and that version?
Yes. You can go through and do a whole ton of variations off of these reagents. You can have lithium borohydride, you can have sodium aluminum hydride. You can even start to change those from being hydrides to other species, which then changes the reactivity of the hydrogen. Okay? So if you look up the reduction reactions with these hydrides, you'll notice there's a big smattering of them, of a bunch of different styles and different ligands on the boron or the aluminum, and they get different reactivities out of them. Okay. We will talk about another one known as dibol. DIBAL. D for 2 for di. IB. Definitely screwed that one up. Let's try that again. Isobutyl. Diisobutyl aluminum hydride. By changing the ligands, we change the reactivity. Dibal now is rather reactive, so it's more reactive than our borohydride, but not as reactive as our lithium aluminum hydride. And it will react selectively for certain carbonyls. Right? We aren't talking about it now strictly because the reactivity of that carbonyl happens to be an ester functional group and it's not a nucleophilic addition. It's an addition-elimination reaction. Okay? So, mechanism. How can we go through and show a mechanism for this? And as a hint, there are a bunch of different ways that you could go through and show this mechanism. What you will typically see as a mechanism is that we will take the electrons, attack our carbonyl. Right? Yeah, good enough. I hear you, give me a second. We'd form the negative charge on our oxygen. Could show the hydride attached. We'd have aluminum H3 floating around. That aluminum H3 has what left over? Excuse me. Technically an empty p orbital. If we want to get really nitpicky with our mechanism, it can end up coordinating to the oxygen. That's really nitpicky. Usually don't expect that. But I will write the aluminum hydride there for a second. We can then move to step 2, add our H+, it can protonate. And we'd have our final alcohol. What happens if we started with the borohydride? Well, pretty much the same thing, except now our intermediate would be BH3. Where would we get our H+ from? Depending on our solvent, it's either water or it's an alcohol. Either way, you get your H+ from the solvent. Okay. Both the boro, or the BH3, and our aluminum H3 still have the potential to react again. That aluminum hydrogen bond is not particularly stable even when we've moved to this state, because remember, officially we could coordinate the oxygen to that, which means every time we add BH4, there are 4 hydrides that can react. Every time we add aluminum hydride, we have 4 hydrides that can react. Okay? So it's going to change some of the dynamics of our reaction. We've got to watch out for that. Okay? So if it came to, say, calculating limiting reagents, you'd have to scale up whatever your borohydride mole was, or realize that you have 4 equivalents of it every time you weigh it out. Okay. Cassie, question?
So would silicon act more, is it used much for a reagent, or like would it act more like boron or aluminum, because it's boron's also on the other side of this?
Why do aluminum and boron react similarly?
Because they're both metal. Or,
Boron is actually a nonmetal.
right.
Actually, yeah, I think it's a nonmetal. It might even be a metalloid. I don't remember exactly. Why do boron and aluminum react similarly? They're in the same group, same column. What would I expect silicon to react like? Carbon. Nothing to do with boron or aluminum. Okay. Why do we get similarities in reactivities within the group? Number of bonds is their reactivity. Why do we get the same number of bonds? Same number or same reactivity? What's that? same number of valence electrons, we're just in a higher energy level. Okay? So within a column with the same number of valence electrons, you get the same types of interactions that can come out of them. Okay?
So what takes something down OR after?
So what then picks up the remaining alcohol OR? Whatever our solvent was, we probably washed that away into our solution, and then we threw it into the waste bottle, and we let hazardous waste deal with it. But officially, you would have a negatively charged oxygen there. And yeah, that would be potentially dangerous to work with. Other questions? Yippee. What does this mean for our reagent conditions? Okay, if we have significantly different reactivity, this means we're going to have to choose our reagents carefully. Okay? What kind of carbonyl are we trying to react with? Okay? If I'm reacting with formaldehyde, the most reactive carbonyl, it probably doesn't make sense to add the lithium aluminum hydride, because I'm now taking the most reactive reducing agent. Okay? That could potentially release a lot of energy and be really dangerous. So I'll use sodium borohydride. Use the strongest thing, use the weakest thing that will still get the reaction done. Okay? That's your general concept for everything. Solvent choice. With borohydride, we can use an alcoholic solvent. With lithium aluminum hydride, we cannot. The lithium aluminum hydride is now so reactive that if there is an acidic hydrogen, the lithium aluminum hydride will act as a base, not a nucleophile. Okay? So let's repeat that. If we had something along these lines, we could probably get away with using sodium borohydride here to do the reduction. We would probably have a hard time using the lithium aluminum hydride, because what would the lithium aluminum hydride do instead? React with the hydrogen on the outside, neutralize itself pretty quickly, and probably in a giant ball of flame. Okay? So we don't want to use the lithium aluminum hydride in that circumstance. Okay? You guys making fun of my giant ball of flame?
Saying it would be kind of fun to do that, so.
I think maybe that's what we do.
No, we don't want to do that. Okay. So your textbook goes through and gives you kind of an interesting version on this. Our lithium aluminum hydride, if we put this in an alcoholic solvent, we get a very fast acid-base reaction releasing our hydrogen gas. With sodium borohydride, that reaction is very, very slow. So if we can slow down that acid-base reaction, we can get the hydrogen acting as a nucleophile. Okay? If it's a very fast reaction, all we get is the acid-base reaction. We don't get that nucleophilic reaction coming in. Okay? Questions? Advance. More on this. What does this mean for our nucleophilic additions? Depending on what we are trying to reduce, we will change the reagent. Okay. BH4 will do all of those. Okay. Or borohydride. Why does it react with the acid chloride? Sorry, that very first one. It's known as an acid chloride. What did we say was the reactivity of that one? Very reactive. So borohydride will react with it. Lithium aluminum hydride will react all the way down to your nitriles. Okay? So if we're trying to reduce the nitrile, BH4 won't do it. Lithium aluminum hydride will. Okay? Preview into chapter 20. We try to name each of these functional groups. First one. Ketone. Next one. It's an ether and a carbonyl, which becomes an ester. And the last one, I just said it, it's an acid chloride or acyl chloride. Okay. So we've got slightly different functional groups. What is the big difference that the last two bring into this that makes a significant difference in reactivity? Particularly if we look at the last one. If I have a nucleophile attack, what was that, Matt? Say it louder. That last one, I have a leaving group in the chloride. The second one, I also have a leaving group. It's not as good of a leaving group, but I also have a leaving group there. And the first one, what's my leaving group? There isn't one. So when we look at chapter 17, 18, and 19, we don't have a leaving group because we're just looking at nucleophilic additions. When we move into chapter 20 and 21, we now have nucleophilic addition followed by elimination. Right? We have to have that leaving group under those circumstances. LAH being so reactive is going to do what to every single one of these? There's nothing acidic for them to react with, LAH to react with. It will reduce all of them down to the alcohol. It is so incredibly reactive, it will convert every single one of those to an alcohol. Ow! Okay. Think about it. That's kind of what's happening when we move forward into chapter 20. Not a big deal for now. So our hydrogen nucleophiles, give you a couple minutes to work through these. If you got questions, raise your hand. All our reagent does is convert it to an alcohol. Straightforward, just make it an alcohol. And I noticed some people going through and showing the hydrogen. Cool, I could accept that. Here's another question that we could throw in here. How many products do you get for that first reaction?
2.
Why 2? That's a stereocenter. Okay, which means the hydride could either have attacked from the top or from the bottom of your pi system. You have a racemic product. The next one. And I'm going to have to erase that and get it out of the way. And I saw a lot of people show the hydrogen. While I would probably accept credit for this, your online homework will not give you credit for this answer. You've specified 3 bonds to that carbon. What the homework is now wondering is what's that 4th bond? Okay. If that H was something else, any other atom than an H, a carbon, I don't care what it was, you would be okay implying all hydrogens. So you imply all or none. So you would have to show both hydrogens or get rid of both to get it correct. Last one, nice little wrench thrown into that one. You had to predict the reactant. Nothing happened to that structure. We've got our last carbon. Borohydride reacts with carbonyls. There we go. Okay. Are there other answers on this one? Yep. We haven't officially talked about them yet, so we won't worry about them. But other answers do show up for that one. Questions on those? Okay. Carbon nucleophiles. There are 3 methods that you already know on how to get a carbon nucleophile. Okay. So let's do one important step, which is always important when it comes to an exam. As soon as you see nucleophile, you should say positive loving, which means it's negatively charged. So I could put that all together and I could say really what I'm looking for is carbon with a negative charge. What are the 3 methods that you already know on how to get a negatively charged carbon? Feel free to talk to the people around you, see what you can come up with. What was that? No, what you said wasn't necessary. So let's resume. What do we got? Anything? It's fine. How can you get a carbon nucleophile? How do you get a negatively charged carbon? Carbene. Fair enough. There are 4 ways. Way to go, Jimmy. Right, and then strong base. No, that's it right there. Yeah. That gets us a carbene. Yeah, it's our diazomethane. Is our carbene.
That's the carbene.
Yeah. Really? Nothing?
You could take acetylene, take a proton off the end.
Take acetylene with a strong base. That strong base needs to be sodium amide or stronger. You now have a carbon nucleophile.
So are there technically 2 H's, but you only drew 1?
Yes, because that could be any R group.
Oh.
Just to call you out, Jimmy, you were actually asking about the formation of one of these earlier today. Yep. Very first thing you did when you came in and asked me questions was actually talking about the formation of a carbon nucleophile. Keto-enol tautomerization gets us a negative carbon. And the last one, which nobody ever remembers, but it's okay. Sodium cyanide, your nitrile. We draw out our Lewis structure on that. Oops. It actually starts negative. Okay. I think those are the only ones that you know as carbon nucleophiles. So this is kind of interesting. We've talked about oxygen nucleophiles, nitrogen nucleophiles, even halogens. Why do we not talk about carbon nucleophiles very frequently? They are very, very hard to make. Okay? So hard to make that whenever we actually make them, they typically pick up somebody's name. Okay? So, not easy chemistry because our carbon is very small and unelectronegative. Okay? The common theme in all of those, our carbon ultimately needed to get bound to something that was less electronegative than it. What is less electronegative than carbon? All of the metals. So for organic chemistry, we would say not much because we tend to focus in organic chemistry only on those 10 elements in the upper right-hand corner with hydrogen. And we think, well, there's nothing less electronegative than it. Well, the entire rest of the periodic table is actually less electronegative than carbon. Okay? So we need to get a metal somehow connected in there. There's a couple ways that we could go through and do that. We saw that with the bases. You could add straight magnesium metal or lithium metal in the presence of a alkyl halide, and that will turn into your carbon nucleophile. Why? The R group is connected to what atom in this case? Magnesium. Magnesium being a metal is less electronegative than our carbon, which means the electrons in that bond spend all of their time on the R group. We have a nucleophile. In the other case, lithium, also a metal, less electronegative than our carbon. The electrons in that bond spend all of their time with the carbon. Okay? Rare, tricky, and useful to deal with. Why are they rare? Carbon doesn't want to be a nucleophile. It's one of the incredible reasons why it's rare and difficult to make. Why is it useful? I can now add carbons to a structure. I can make the structure bigger with carbons. That's pretty incredibly useful. Why tricky? Kind of not really. We're saying we're making a nucleophile. Nucleophiles are also bases. Guess what all of these reagents act primarily as first? bases, which means everything we do in the process of making these reagents has to be in a neutral or basic environment. We cannot do it in a remotely acidic environment, okay? Which makes it tricky to deal with. Okay? We will pick up there. Sorry, I ran 2 minutes late.